All right, so this is about how to generate code from type signatures of functions. And I actually will just, it is a presentation that I've given before. I will just show the library that I implemented and explain how it works. And so I'm just going to load the dependency. Let me see, I've done this presentation. Okay, so I'm just importing this library. And the necessary symbols. And then I'm going to start by implementing a function with a type signature that is reasonably easy. Let me just do that. Okay, just for convenience. Okay, so imagine you have a function that has two type parameters. And it has this type signature that looks like this. Okay, so how would you write code for this function? Well, you are supposed to return a pair of A and A types. So, and it's a type parameter. So how can you get the value of that type? Well, you can't really unless you have it already. And we only have one here, which is X. So the only way to implement this type signature is to return a pair of X and X. So why do I need to do this if there's only one way of implementing this type signature? I just do this. And a Scala macro called implement examines my type signature and expands into the Scala code that I want. So let me test this. So f is a polymorphic function, right? So I'm going to test it. So I'm giving it 2 arguments. And I can interchange these arguments. And so that's the code we expect. Let me give you another example. I can define functions in many different ways. Type signatures can be written in different ways. So for example, I can write a type signature like this as well, as a curried function. And again, in this case, there's only one way that you can write this code. You must ignore the second argument. It's the same as the first one. You must ignore the second argument, and you must return the first argument. So this should work as well. And you see the type is correct. So yeah, so basically it replaces the need of writing code that is uniquely following from the type signature. Let me give you another example, which is in my slide here, which is this. So you're familiar with the reader monad. So this type signature is basically the map function for the reader monad. Let me just call this whatever. So it can implement this. But if I try to define a function that has a type signature that cannot be implemented, such as this one, and this cannot be implemented because basically I screwed up with types, and I thought I was defining map for the reader monad, but I used the wrong type parameter. I'm trying to map on the contravariant type parameter, and that doesn't work. And so you cannot actually generate code for this function, because in order to generate an A, you need to call this function on an E, and you don't get an E anywhere. So if I try to do this, EA, EF, FA, then it's an error, and it's a compile time error. And it tells me that the type cannot be implemented. Another example where there's an error. Let me call this whatever, x2. It's not going to be defined, so it's not going to work anyway. So in this case, it can be implemented, but there are two different ways of implementing it. I can return x, or I can return y. And there's no obvious way of choosing one over the other. So they're both equally good somehow. So if I do that, it tells me this type can be implemented in two different ways, in like this and like this. And there's no, so in fact, this library tries to be more intelligent, and it tries to assign scores to different implementations. The score, as you see here, is a tuple of numbers, and it doesn't matter what these numbers are, but this score is actually a penalty for losing information. And that's a heuristic that the library uses. So the idea is that you can have different implementations. So let me show you a case when this works well. Okay, so the case where it works well is if you have an option of A, and you want to map it over to B, and you want to get an option of B. Oops. Oh, I forgot the type parameter. Sorry about that. So this works. Okay, so I can generate the code for a map function for option. Let me check that it works actually. Let me see, sum 1, 2, 3, and x going to x plus 1. Let me see what happens here. Sum 1, 2, 4. So that's what you expect, right? But actually, this function could have been implemented by simply always returning none. And the type would be correct. There's no question. The type is correct, but this is not what we expected to do. And actually, such a function would be kind of useless. So the library is trying to figure out which implementation is useful. And the score it assigns is the information loss score. So the heuristic is that if you implement this function by always returning none, then you're discarding all the information in the arguments. You're not using the arguments at all. And another implementation uses both arguments. And that's better. That's the heuristic. It's better not to discard arguments. And the number of arguments that you have discarded is a penalty, which you have seen here in the score equal to 1, 0, 0, 0, 0. So this 1 is one argument that you have discarded in this implementation. Now, sometimes you cannot but discard arguments. You cannot help it. But that's fine, because it's just a score. And you choose the best score, and that's your implementation. So another example of when this works kind of the way you expect is, let me define some function where x is a tuple AA, and you return tuple AA. So what does it do? Well, it's an identity function. But why doesn't it interchange them? That would be another implementation of the same type. Because there's a penalty on losing the order in which you had the tuple elements. And that's another heuristic, of course. But so there are some heuristics like this. So you don't want to lose information that you're given. I'll give you another example where this works. So this function can be implemented in infinitely many different ways. Yeah, you can ignore f and just return x. Or you can apply f to x. Or you can apply it twice to x. Right? Now, again, heuristics here do not allow you to ignore arguments because you have another implementation that doesn't ignore arguments. But it does not look at the implementations that apply the same function many times for no particular reason. If you don't have to apply that function. So this implementation is basically applying f to x. So that's the kind of thing that it can do. It can also do, it supports case classes, it supports all kinds of type signatures, and it also supports specific types like int and string, but it treats them as opaque type parameters. It doesn't know anything about int. It won't try to guess for you what you want.
Does it have access to things that are available in the scope and not just parameters?
Yeah. So the question is does it have access to other values available in the scope? That is not easy to do in macros. So the only thing it knows is that if you're defining a class method and a class has some things in its constructor, it can see those things. And it also can see other class methods that you defined previously. Not the ones that you defined later, but the ones that you defined before. You can use those. So yeah, so that's how it works. Yes.
So for your example that takes two A's and returns an A, if it was like a monoid, would it know that hey, I could append these to preserve?
Yeah. So the question is, if I had a monoid, would it know that it can combine things from a monoid and use operations? No. So that kind of thing, I believe, is beyond the scope of what should be done using this mechanism. Because once you start doing those computations, those are not specified in the type. So there are many different ways that you can do things with monoids. Once you have a monoid, first of all, you can always return its empty element. And there's no type information that prevents you from doing that. Well, you might have these heuristics that tell you that you're not using some information, but then there are too many options. And also, it doesn't know about monoids, doesn't know about any type classes. It doesn't know anything. It just looks at plain types because there is no theory that tells you how to derive implementations from types for some kind of general type classes. So now I'd like to talk about theory behind this very briefly. What is the algorithm? Yeah. This is another API. There are several APIs. So this API is an expression-like API. It's not a function definition API, but it is an expression. So of type, then a type parameter, and then arguments. It's an expression that only it returns a result. So there's no type signature, except you have to give it here. So on the left, there's no type signature. It's not a method. So basically, you say, given these things, can I get a value of type result? So here's an example. I'm given a string ABC. I'm given a function from string boolean to int. And I'm given a true. Can I get a value of type result, which is a case class having an integer and a string inside? You can, because you have a string, and an integer you can get from a string and a boolean, and you have also a boolean. So all you need to do is you put f applied to this ABC and to true. You get an int. You put this int here, and then you put the ABC here. And then you construct the case class. And that is, again, derivable from types. And so that's kind of an expression-oriented API that you can also use. If you have a bunch of values and you think you can just combine them somehow, to put all the type classes, maybe, option, whatever, you don't care, then it can do this. And again, if there is more than one implementation, it will be a compile time error to do that.
Doesn't try and rank them?
Sorry?
It doesn't try and rank them. There has to be exactly one implementation for this?
It will rank them. It's the same idea. Sorry, yes, I should have said that, yes. So it will again try to rank them. But if there's, even besides ranking, if there's still ambiguity, then it will be an error. Now, there are other things that I tried to do here. I wanted to actually reason about Lambda terms here, but let me go through, first let me go through the algorithm. Now, these are other examples. Let me go through the theory behind it. So there's the Curry-Howard correspondence, which is that propositions are types and proofs are programs. And the correspondence looks like this, basically, that if you have some proposition in logic where you have, say, for all A, from A follows true, or something like this. Then there corresponds to it a type signature of a function, or some type signature, where instead of true, you have the unit type. Instead of entailment, implication, you have a function type. Instead of disjunction, you have the either type. And instead of conjunction, you have the tuple type. So let me see if I have this in the previous slide. Are you familiar with the Curry-Howard correspondence? OK. So maybe I don't have to explain this. I mean, so anyway, so here's what the library does. You give it a type signature, like this. On the right-hand side, it's a macro. This macro can read the type that is inferred for it by the compiler. The type is this entire type signature. 3 type parameters. So via reflection, the macro can introspect on the type and come up with a syntax tree for the type expression, which will have these type parameters, and then there will be this, this, and this. So then it will be some kind of type expression containing function types, products and coproducts, and type parameters, and ground types, like integer, string, and so on. So this is the first step. So you have this type expression as a syntax tree. Then it's translated mechanically into the logic expression, where you, for every ground type and for every type parameter, you introduce a new proposition variable. And then function types become implications, products become conjunctions, and coproducts become disjunctions. So then you have a logical expression, and then you add these quantifiers for all type variables. So then you have a theorem like this. out of this kind of type signature. The next step is to run a proof search for this theorem. So there is a formalism and an algorithm for finding possible proofs. And this is the intuitionistic logic. So this algorithm is this intuitionistic propositional logic prover, which I'll try to see if I have a pointer to the paper. I'm not sure I have it here. Anyway, there's one particular algorithm that everybody is using, which is called LJT, and it took a very long time for mathematicians to come up with that. So I'm not trying. It would be kind of hopeless to try to invent it again. So this is a set of rules for inference, such that they generate a finite search space for you to go through. So this is. Can you read this notation, or not so well?
Not so well. Is it? So it's a defined transformation that you're doing.
So okay. So gamma is a context which is any number of other things, assumptions. So at the top there are assumptions. At the bottom there is what you derive from them. So these are derivation. So at the top there are two assumptions here, and the bottom is what you derive from these assumptions. Which means that if you're looking for a proof of something, then you look at the bottom. Is any of these rules such that the bottom looks like what you have? And if so, then you need to prove these things at top first. And then you can prove the thing at the bottom. And then you look at these things at top, and that may be more than one thing that you have to prove now. So you have then more things to search for, and that's a kind of a tree. Or maybe just one thing that you now have to search for. So then you generate this tree of things that you have to prove but every time they're getting simpler, because you're kind of, everything on top is always simpler than what's on the bottom. So there may be more assumptions, more things that you need to prove, but each one of them is shorter. And finally, you would have very short things to prove, like prove A, and I have A. And that you can do. So once you get there, you go back, and you actually assemble all these proofs into one giant proof. And then the next step, well, I'm going to skip this. And the next step is to generate code from the proof. So here's how it works. Each rule, let me just go back here. So for example, this is a rule. If you want to prove A or B, then you have to prove A. Sorry, you have to prove from A or B follows C. That's what you want to prove. Then you have to prove that from A follows C, and you have to prove that from B follows C. But suppose you proved that, these two. How would you get a proof of this? Well, a proof of this is an expression of type A to C, a function A to C. Because this symbol is basically plays the same role as function arrow, because it's on the left of this symbol are assumptions, on the right of this symbol are things that we prove from those assumptions. And so you have a function from A to C, and you have a function from B to C. How can you make a function from either AB to C? Well, that's a case expression. You match on either AB, and if you have an A, then you use that first function that you already have to get a C, or you use the second one. Now, the case expression is a specific piece of code that you have to insert at this place. And in the case expression, you also insert the proofs that you had before, which are previous pieces of code that you assembled. So in this way, you assemble Lambda terms piece by piece as you go from the proof to the code. And so finally, each rule of this calculus or whatever, each rule corresponds to a specific construction of the code of the lambda calculus. So this is a case expression. This is a function application, because you have a function from A to B follows C, and then from A to B follows A, from B follows C. So you have an A, then you put that A into there, you get a B, and you finally get a C. So that's a function application, that's lambda abstraction, that's a projection of a tuple, and so on. So basically, you have little pieces of code that you assemble. As you found the proof, you can then build up this code that corresponds to it. And by definition, what happens is that the type of this code expression will be the same as the logical formula that you proved. Because the whole point here is that the proof means that you can write code of this type. Because that's what the Curry-Howard proposition is. To each type, there corresponds a proposition that you can write an expression of this type. And that is a proof that you can. You're writing it. So my library then assembles this lambda term piece by piece, simplifies it, so you get something like this. And then, so here's an example. This is the formula that I want to implement. This is the type that I want to implement. And this is the lambda term that has this type. And then I transform that back into Scala code from pure lambda calculus, which is, again, it's just a mechanical step. But I have to put in all these syntax and constructors and case classes and case objects and so on and so on. So all this is not present in the lambda calculus, and it is extra. It has to be put in. So that's the last step. And finally, for each proof that I find, I have also a score, because I have symbolic information about the code, and I can see how many arguments I'm dropping, or there are other heuristics like do I generate every possible case class from a sealed trait, or only some of them, and something like that. So because if I don't generate some case classes from a sealed trait, then I'm maybe not using all the information I had, right? Because I had some information, now I'm supposed to generate one of these case classes, and I always generate one of them. Maybe another implementation generates all of them, and that's better. It's all heuristic. But anyway, so I can do this because I have symbolic information about the code. It's not compiled yet. It's a syntax tree still, so I can walk it and analyze it in all kinds of ways before I put it back and let it be compiled. So that's how it works. So finally, I have a list of possible implementations ranked by the score, and I see if there is just one with a top score or more than one, and then I make a decision. Or maybe there are none. Maybe there is no implementation. And then I make a decision, and that's all happening at compile time. So, all right. So that's basically all I have. Oh yeah, here are these articles. So there are these papers that explain how this algorithm works. And this is the only paper that makes sense to anyone, really. This is another useful paper that basically explains a little more about how to implement this. But again, these people don't necessarily, they don't explain everything very well. So but anyway, so that's what it is. This algorithm allows you to generate, oh yeah, that's what I wanted to say. This algorithm allows you to generate code from type signatures as long as the type signatures are built up from these three constructions, product, coproduct, and function. There is no notion of recursion. You cannot generate recursive code. There is no notion of type class. You cannot generate functor code or monad or anything like this. You cannot say, oh, this is a monad, therefore I can use flat map or something. There's no such thing. There is no way to even encode that because it's not propositional. It's higher order type. It's a type class on a type constructor. So it's not just a specific type that has specific operations. Because you could have included these as your values from which you build. But those values are not just values for a monad. These are actually type constructors. The flat map has type parameters itself. And there's no algorithm that can solve those problems. So there are these limitations, certainly. Another thing that I have implemented is reasoning with Lambda terms, with Lambda calculus directly. Because what I wanted is to generate type classes that obey the laws. So for example, option, we just saw I can generate map for option. So I can try to generate flat map for option as well. It works. But how do I know it's correct? So there I had some heuristics. That's very nice. But what if it's wrong? Despite the heuristics. Maybe the heuristics didn't work correctly in this case. I want to choose the correct implementation. I want to check that this implementation is correct. So FM, that's not going to work like this. Let me try something else. Option A, option B. Let me do it like this. So I implemented something called Lambda term. And this is basically a utility. So this fm1, actually, it looks like a function. But actually, it is a subclass of function secretly that has this lambda term property. So actually, I put the symbolic lambda term right there next to the compiled function code. And then I can reason about it at runtime, but symbolically. And so I can print it. And the lambda term itself is a bunch of case classes. Let me try to show you what that is. Yeah, this is a bunch of case classes which represent the lambda calculus. These are string representations of varying prettiness that you can use for debugging. And basically, you can write code that will symbolically verify the laws of a monad for this code. So if you don't think that this code is necessarily correct, then you can write symbolic verification of the monad laws. And so because all the code, you have it symbolically. It is not just compiled. It is compiled for you to use, so it's fully compiled and fast and all that. But it's a class that has an extra value in it, which is this case classes representation of the lambda term. And it's a tree that you can reason about. So that was that's the extent of what I have done. And that's it. So we're out of time. And thank you.
Have you tried to generate, run this through Scala Meta to generate source code for the generated that you generate from the macro?
So the question is, did I try to use Scala Meta to generate Scala source code? No, I don't know enough about that, and I don't know enough about how I could do something with Scala meta. I'm generating Scala code in the macro in the usual way using quotes, and I don't know what else I can do and why I would use Scala meta.
So what I'm thinking is it would be nice in an IDE to be able to say like implement and then have it give me a drop-down list of possible implementations.
Right.
And scroll through them and see which one looks like the one that I like.
Right.
By the ranking.
Well, if you're interested, let's work on it. You know? I don't know much about how to do this.
And neither do I, but it sounds like it would be fun.
But it would be very nice to have an IDE plugin that could do this.
Pretty awesome. Are you familiar with the Idris IDE? How you can it just like instead of typing implement, like you have a hotkey and it will just write the code. It's very similar, but it's just they've tied it into the.
Yes. Well, so they have an algorithm that's very similar to this one, and I believe with similar limitations. Unfortunately, I don't think there's an algorithm that will do what you want in a lot of cases. Also, the proof space is very large sometimes. And it's a very slow algorithm because it goes through all possible proofs because it wants to find the best implementation. So it doesn't just take one and stop. If you just want one, you can cut all kinds of corners. But if you want to find the best implementation, maybe, I don't know what Idris does. I think Idris just finds up to the next type hole or something. And yes?
Can I parallelize the proofs with chemists?
Right. So the question is, can I parallelize the proof with chemists? So I can, probably, but I didn't want to do it at this stage because, right now it's kind of a proof of concept thing. Also, it's a macro. It runs at compile time. So I could certainly make multi-threaded search, and it actually makes sense. It's a search tree, and chemist can very easily express that kind of thing. It's a parallel tree that does something and then comes back. I didn't do that yet. And I'll think about where this entire thing is going before, sometimes the IntelliJ is just completely stuck trying to do this, and Scala compiler is doing a lot of work at compile time here. Yes, it could be parallelized. Sometimes it could be actually a win. But yeah, so chemist is very easy to use for a computation like this where you have a tree. However, I didn't have enough time to do that yet.
Could you do it in under 15 lines of code in chemist?
The fork join is certainly about 10 lines or so, yeah. The entire fork join, implementation. Just the functions that you do in forking and joining, of course, can be very large, but the parallel logic itself is quite small.
This is awesome. And I think the Idris one thing it does, I think, is it has the defs for everything that's in like the standard lib, right? So for your flat map example, I think that it would generate what it thinks it should be, and then just say that already exists. Like the definition would be like equals flat map or something, which is kind of neat.
Right. Well, you could certainly try to. So the question is, Idris knows about the standard library and offers you implementations that are in the standard library. Yes. So Idris maybe does this for various reasons. I didn't try to do this kind of search based on type. You have a type. Is there something in the standard library with this type? I didn't try to do this. Actually, my next step was to reason about the laws and to generate type classes that automatically satisfy the laws. So that you say, you know how in cats you say a new functor and then you have to write the stuff? I want to say equals implement. New functor, new monad, whatever type class can be generated. I don't want to write all that boilerplate. The macro can read this. It can know about cats, and can understand that you're trying to derive a type class instance, and that all can be derived automatically. In many, many cases, automatic derivation of type classes is way easier than this because there's no search tree in most cases. In some cases there is, but it's very short. It's not exponential. So in some cases you have to search through certain things, but nowhere as complicated as this search tree. That I can just make it die very easily if I just derived for you the flat map for option, right? If I put some complicated type here, like this, okay, good. It found that it's a problem. But if I make it a C and so on, if I try to just to make it a complicated type, which is conceptually as simple as this, but it just got more option inside, more tuples inside, and so on. This exponentially blows up the search space. And since it has no idea what I'm trying to get, it doesn't know what flat map means. So it doesn't know, oh, you're just doing flat map for this complicated thing. Let me do it in 1 second. It doesn't know that. So it will just mechanically go through all possible implementations. There could be a lot of them that sometimes ignore some part of the option, and they are going to be higher. They're going to be discarded. So none of that. And then it's just going to go out of memory. Anyway, I think we're out of time. So thank you very much. Yeah, thank you.